Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review everything covered in week 7. So we started our journey with calculus, and to understand calculus, we need to understand the concept of limits. So when we're talking about limits, we just abbreviate it as LIM, we're saying what happens to the value of a function when its input, usually x, approaches a certain value. So I've here drawn the graph of this function y equals 1 on x minus 2 plus 3. So what happens to the value of this function as x approaches 1? Well, you can see as x gets closer and closer to 1, y gets closer and closer to 2. This is a really simple limit. To evaluate it, we could just substitute x equals 1 into this equation and we but what about these limits, x approaches 2? This means x approaches 2 from the negative side or the left. So x equals 2 is here. So what's happening is x approaches 2 from the left, y is getting more and more negative. It's approaching negative infinity, whereas as x approaches 2 from the right, the function is getting larger and larger or going to infinity. So really, as x approaches 2, the value of this function is unlimited. Now note that we got a different answer when x was approaching 2 from the left than when it was approaching 2 from the right. And that's because we know that this function is discontinuous at x equals 2. So this didn't happen at x equals 1. When x was approaching 1 from the left, we got the same as when x was approaching 1 from the right because the function is continuous at 1 but discontinuous at x equals 2. Now, as x approaches infinity, another way to think of that is what happens as x gets larger and larger. So x gets larger and larger as we go along to the right on the x-axis. What will happen is y will get closer and closer to but never hit this asymptote of 3. So we say that the limit is equal to 3. That means as x gets larger and larger, y gets closer and closer to 3. So sometimes you'll have to evaluate limits like these. So these aren't easy. Unlike, say, up here, we can't just substitute x equals 3 into this expression because then we'd be dividing by 0. So sometimes what we have to do is factorize. So if I factorize the top, I get this expression here. Now, because there's an x minus 3 on the top and the bottom and it's being multiplied, I can just cross them out. So the limit of this function here is the limit as x approaches 3 of x plus 3. I can just substitute x equals 3 into this expression, and of course I get 6. So what that means is as x gets closer and closer to 3, the value of this function gets closer and closer to 6. Now let's have a look at rates of change. So here's the conundrum. We have a function like y equals x squared, which is a pretty simple function, and we want to know about its rate of change. The thing that makes it difficult is that the rate of change isn't constant, unlike it is in a linear function. So for example, over here, we would have a negative rate of change because as x is decreasing, y is increasing. Over here, the rate of change is positive. As x is increasing, y is increasing. And around here, the rate of change would be very close to 0. There's almost no change in y values if we change the x values. Now, it turns out that for y equals x squared, the rate of change is different at every single point along this curve. So how do we figure this out? So let's say I want to find the rate of change at this point here, which is the point 1, 1. So, because lines are easy, what I can do is I can draw a line that goes from here to another point on the curve. Let's say this one there. So I can approximate the rate of change at this point by finding the rate of change of this line. And of course, you know, the rate of change of a line is just the gradient. So this green line here is called a secant. It passes through 2 points in the curve. So I'm just writing the general form of the points like this. This formula here is just the gradient formula, y2 minus y1 over x2 minus x1. Of course, x plus h minus x is just h. So what I mean by h is the distance along the x-axis between the 2 points. So in this example here, h is 2 because the x distance between this point and this point, I've gone across 2. And here I'm just letting x equal 1. So this is f of 3, which is 9, minus f of 1, which is 1, all divided by h, which was 2, and the answer is 4. The gradient of this green line is 4. Another way to say that, the average rate of change of y equals x squared between x equals 1 and x equals 3 is 4. But see, the problem is that's just an average rate of change. I wanted to know what the rate of change is at this point. If I want to know the rate of change at just one point, it's called an instantaneous rate of change. See, the problem is this line here in green isn't a good indication of the direction the curve is going at x equals 1. So what can I do about that? Well, what if I reduce the value of h, the distance between x values, to 1? See, this red line here does a much better job of approximating the rate of change at this point than the green line does, because the red line is closer to the direction of the curve around x equals 1. But I could keep reducing h. I could make h like a half. The distance between x values a half. So you can see now this blue line does an even better job than the red line of approximating the curve around the point x equals 1. And in fact, if I keep reducing h, if I keep making the distance between my 2 points smaller and smaller, I will keep getting a line that is a better approximation of the direction of the curve around x equals 1. And that's what we do with instantaneous rate of change. This formula here, this part, is exactly the same as this. But this limit as h approaches 0 says that I'm taking 2 points and I'm making the distance between them so small, so close to 0, that those points are basically 1 point. So if I want to find the instantaneous rate of change, the gradient of the curve at just this point, I pick 2 points that are so close together and I find the gradient of the line between those 2 points that are so close together. Because the points are so close together, this line is becoming a tangent. So let's look more at this formula. So this formula that you saw in the previous slide, we call it first principles. Here, f-x means the derivative. So if I have a function like fx equals x squared and I want to find its derivative, I can put it into this formula here. So if that's f of x, when I find f of x plus h, all I do is change the x in the formula to x plus h. So f of x plus h is x plus h squared. So expanding this gives me that. So to find the actual derivative, I'm now going to substitute in. It will be f of x plus h minus f of x over h, and then you take the limit. So we've got limit as h approaches 0 of f of x plus h minus f of x over h. So x squared minus x squared, they just cancel out. Now what I do here before taking the limit is I divide by h. I can't just substitute h equals 0 into here because I'd be dividing by 0. So I go 2xh divided by h is just 2x, and then I go h squared divided by h is just h. So now I can substitute h equals 0 into this. That will just leave me with 2x. So what does that mean? The derivative of x squared is 2x. That means if I want to find the instantaneous rate of this curve at any point on the curve, I just substitute in the x value and times by 2. So for example, the derivative at x equals 1 is just 2 by 1 or 2. That's the instantaneous rate of change I was trying to calculate on the previous slide. All right, let's try something like this. We're going to use first principles again. So if this is f of x, to find f of x plus h, I just take x in the formula and replace it with x plus h. So now once again, I'm going to need to expand this. To expand this, I'll need to use Pascal's triangle. So this here is f of x plus h, so I'm now going to substitute that into this formula here. So derivative is limit as h approaches 0 of f of x plus h minus f of x over h. So we can cancel out a couple of terms, x to the power of 4's cancel out, and so do the x's here. So our next step, we can't substitute h equals 0, otherwise we'd be dividing by 0. You need to divide everything here by h. So I've taken each term one by one and divided by h to get this. Now, if I take the limit as h approaches 0, anything with a h in it becomes 0. So I'm just left with 4x cubed plus 1. The derivative of x to the power of 4 plus x is 4x cubed plus 1. So the derivative of a function is a function. And in this derivative, I can put any value of x, and that will tell me the instantaneous rate of change of this function at that point. All right, let's look at a quicker way to differentiate. See, we don't always want to use first principles because, as you saw, it can take a long time. So what we found from first principles is when you're differentiating a power function, you just move the power to the front and decrease the power by 1. Now, using this in combination with these three laws actually makes things really easy to differentiate. So I will explain all the laws by differentiating this function here. There's no way I'm going to put this into the first principles formula. That would take forever. So when you have a function like this with heaps of terms, we're going to differentiate term by term. So the derivative of 4x cubed, what I do is move the 3 to the front and decrease the power by 1. So this law here says if you've got a coefficient out the front, you can kind of just leave it. So I just leave the 4 alone, move the power to the front and decrease the power by 1. Similarly for this next one here, note this is a negative 3. I can leave the negative 3 alone for now, move the power to the front and decrease the power by 1. So what would be the derivative of x? Well, remember x is the same as x to the power of 1. So if I move the power to the front and decrease the power by 1, I just get 1 x to the power of 0. Now, this law here says when you differentiate, constants vanish. So this here is just a constant term. When I differentiate, it just goes away. You see, adding or subtracting constant does absolutely nothing to the derivative. Remember, the constants shift a curve up or down. They don't actually change how quickly the function is increasing or decreasing. So that's why this one is just going to completely go away when I differentiate. So how to differentiate something like this? Well, note 1 over x is x to the power of minus 1, and I can use the same rule. I'm going to move the power to the front to make it a minus 1 and decrease the power by 1. So how do I differentiate something like this? Well, I want to write it as x to the power of something because they're easy to differentiate. I can write this as minus 3. Now, the fourth root of x to the power of 3 is x to the power of 3 over 4, but because it was on the bottom of the fraction, it's a negative power. So how I'm going to differentiate this last one, I'm going to leave the minus 3 by itself for now. I'm going to move the power to the front and decrease the power by 1. So negative 3 over 4 minus 1 is minus 7 on 4. So just making this easier to work with, 4 times 3 is just 12, so it's 12x squared minus 6x. 1x to the power of 0 is just 1. Minus 1x to the minus 2 is minus 1 on x squared. And this one here, the two negatives make a positive. It can become positive 9 over 4. Now, x to the power of 7 over 4 is the fourth root of x to the power of 7. And we're done. That's how you differentiate quickly. All right, let's look at a quick applications question. So water is being poured into a tank, so the volume is given by this function here. V is in litres, T is in seconds. How quickly is the volume increasing after 10 seconds? This is asking us for an instantaneous rate of change. So how quickly something's increasing or decreasing is a rate of change, and I'm asked for the rate of change at a given instant, 10 seconds. I'm not asked for the average rate of change over the first 10 seconds. I want the rate of change at exactly this instant. So all I need to do is differentiate this function. Now this function might look different because I've got a v instead of y and t instead of x, but we differentiate it the same way. So we can write this as v dash, or the derivative of v with respect to t. Either way, these mean the same thing. So same idea, I'm going to move the power to the front and decrease the power by 1. When I differentiate, constants like this 200 here just vanish. So this is the rate of change of the volume. It's 0.4 times whatever t is. So if t equals 10, because t is in seconds, then the derivative is 0.4 times 10, which is 4. Now, because V was in litres and T is seconds, this is 4 litres per second. It's positive, so the volume is increasing at a rate of 4 litres per second at this instant. After 11 seconds, it'd be increasing at a different rate, because this is an instantaneous rate of change. All right, thanks so much for tuning in, and sorry about the long video. This has been the luckiest maths teacher in the world. Have a great day.